Questions from you guys on stuff? Blake?
Can you do number 9 for 2.7?
2.7, number 9? I sure hope so.
Yeah, I couldn't do it, so if you can't, I don't blame you. What? I mean, then, I don't know, it was hard.
It says, find the slope of the tangent line to the curve, yada, 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 at x equals a. Okay. It's just going to be a hassle, but we can do that. Oops, that was a 2. All right. So part A. So the derivative at a is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. That's just the definition of a derivative. So go ahead and plug that in. We'd have we have the limit, Mr. Kulak, don't forget your limits. 3 plus 4 times a plus h minus 2 times a plus h cubed minus the quantity 3 plus 4a squared minus 2a cubed all over h. Yes, sir. Thank you. So far, so good, Blake?
Yeah.
Hopefully you noticed at the first step, if you would have tried direct substitution there, you would have ended up with 0 over 0. So that's why we continued plugging things in, and we're going to have to try to do some simplifying before. If we couldn't plug it, if we're going to do a direct substitution there, we haven't done anything yet. It's still the exact same thing, so we're just going to kind of keep on grinding algebra here. So I'm going to go ahead and FOIL this out and distribute the 4 through all in one step. Is everybody okay with me doing that? Okay, 4a squared plus 8ah plus 4h squared. I'm going to do the same thing at the next step. I'm going to FOIL that out and distribute the negative 2 through. So it's negative 2a cubed minus 6a squared h minus 6ah squared minus 2h cubed minus 3 plus 4, minus 4a squared plus 2a cubed all over h. All right. Now let's combine some like terms, and hopefully we can do some canceling and reducing here. I see I have a minus 2a and a plus 2a cubed. Those will cancel out. I have a minus 4a squared and a plus 4a squared. Those can cancel out. I have a minus 3 and a plus 3. Those can cancel out. And then if I look closely, I'll notice that everything left has a factor of h in it. So I can reduce an h from all of those and out of the denominator. Now let's just see what we have here. So that's what we got left. Minus 2h squared. And if we do our direct substitution now, we're left with just 8a minus 6a squared. So that's my f prime of a. Want to hear something exciting? Yeah. In like 2 sections, you're going to be able to do that problem in your head. instead of having to do all that grinding that we just did there. It's going to be like the greatest day of your life. Because Mr. Kulik could look at that f of x and find the derivative without having to write anything down in between. And you can too. I just have to show you how to do it. Blake.
Sorry, this is going to be another question. This one's really easy.
Well, this had more parts to it.
Oh, it did? Oh, shoot.
There's parts A, B, and C.
Oh.
Do you want me to go through A, B, and C?
I guess I was even more or less than I thought. Yeah, sure.
Okay. It says, find the equations of the tangent lines at the points 1, 5, and then 2, 3. So we'll do this one first. The slope for this is going to be just me plugging in 1 into my derivative that I found before. So y minus y1 equals m times x minus x1. So that's going to be 2x plus 3. It's 424 minus 16, that's negative 8. So y minus 3 equals negative 8 times x minus 2. So we get y equals negative 8x, that's plus 19. And then part B says graph the curve and both tangents on a common screen. Okay. If we must. 3 plus 4x squared minus 2x cubed. And then this one will do 2x plus 3. Do that, make this one a thick line, and then negative 8x plus 19. And we'll make this one the dashed line. And I guess as long as we're doing this and being all fancy, let's plot these points 1, 5 and 2, 3 so we can see exactly where these tangents are supposed to be going through. How's that sound to everybody? Mr. Kulik, you're fancy. Yeah, I had the axes off from earlier, so I'm turning those on. And my window's all goofy, so I'll just do a zoom standard. Okay, so there's my function. There's my first tangent. There's my second tangent. That all looks pretty good to me. Woo! Victory. What up now, guys? Luke?
Please explain 17.
Same section?
Yeah.
Okay. Let's just do this. Not ready to do this quite yet. All right. We're on what? Page 151. I'm just going to go screen clip the picture rather than try to draw the graph because it's kind of a lot less work, but it takes a minute to search. All right, there we go. For the function g whose graph is given, arrange the following numbers in order, in increasing order, and explain your reasoning. Okay? So I'm just going to talk through the reasoning. I'm not going to write anything down for that. Okay. So I'm going to have 0 in the middle because, well, negative things are going to be left of that. Positive things will be to the right of that. The rest of these are derivatives. So at -2, we're looking at that slope, which is pretty positive. That's pretty positive, right? It's pretty steep. Okay. At g of 0, that's negative, and that looks like -1-ish. If I was to eyeball that, this slope might be +2 or 3, something like that. If I look at g prime of 2, that's also positive, but it's not as steep as that other one, so maybe I'll call that a +1. And if I look at g of 4, that's this slope, which is even less. So maybe I'll make that 0.5, but it's still positive. So if I was to write this, I would have g prime of 0, because that one's negative, 0. And then my least steep part is g prime of 4. My next steep or least steepest part is g prime of 2. And my steepest piece was g prime at -2.
So when you're looking at a derivative, are you also kind of like looking at the slope of the tangent line?
The slope of the tangent line is the same as the value of the derivative at that point. So all I'm doing here is just drawing in my tangent lines and using those to estimate the slope. And I don't even really need an estimate in this case. I just need to like rank them from steepest to not, to shallowest or whatever. And that's good enough. But yeah, the slope of a tangent line is equivalent to the derivative at that point. Talking about the same thing. And that's the key to cracking that in just a couple of minutes or whatever. Anise?
You do?
2.3?
Yeah.
Okay. Sure thing. Okay. All right. I'm going to screen clip this one, I think, also, just because it's the piecewise function is pretty big. And I just honestly don't trust myself to like copy it down correctly without having to look back and forth about 16 times. Oops, that's not what I wanted it to do. Try it again. Put that in a reasonable place, and now screen clip it. Okay. Here it says evaluate each of the following if it exists, and then sketch a graph. So what I need to do is I'm going to be using this down here. Is going to tell me which part of the domain I'm working in, and then I can just use a direct substitution to get with the function to get the value of these limits. Is that okay, Anise?
Yeah.
So for example, part I is just going to be 1, right? Cool with that? Okay. If I go to part II, so here, the value prior to the point is 1. I have to check the value after the point. Here, let me write down y. So I know the limit as x approaches 1 of g of x only exists if it equals the left-hand limit n is equal to the right-hand limit, right? So we know that this is 1. We already did that. To do this piece, I need to look here. So I'll just be plugging in. So 2 minus 1 squared is 1. So that limit does exist, and it is equal to 1. Is that okay?
Yeah, you're always plugging it into the
Well, it's because I needed to, since this is the limit as x approaches 1, I need to check the left-hand limit and the right-hand limit. So the left-hand limit we did in the previous problem. The right-hand limit is going to be when 1 is bigger, when we have the bigger side of 1, so I had to pull that piece. Is that okay? And because those matched, I know what the limit is, and I know it's the same thing as those two limits. Even though the value of the function at 1 is 3. Right? And which is what we're going to see here in GII. Right? That's just 3. Since there I just go. Is that okay? Okay. And then let's erase some of the stuff there. The next piece is 2 from the left, so that's below 2. So I'm going to be over here. So when I plug 2 in for that, I get 0. And when I go from the right, then I'll be over here. When I plug that in, I get negative 1. And then if I want just a limit as x approaches 2, that does not exist because the left-hand limits and the right-hand limits were different. Okay with that? All right. Now to sketch a graph of this, I'm going to make an XY table for each of the parts. So if I look at that first part, that's just a piecewise function, or a linear function. So I just need 2 values of x from the domain. One value of x should always be the end of the interval, or the end of the domain. So I'm going to use 1. And the other could be anything less than 1, so I'll just use 0. Then I'm going to take that second part of the domain. I'm not worried, or the second part of the domain I'm not worried about because it's just a single point. Because it's just the value when x is equal to 1. So it's just one value. It's just a single point. So I don't need to worry about that. Well, I do when I graph it, but like, it's not going to be a problem. If I look at the next part of my function, I notice that this is a, what type of function? Quadratic. To graph a quadratic function, I need to include vertex and 1 point on each side. However, the vertex here is, for this quadratic, the vertex should be, nope, that's the y-intercept. The vertex is 0. Remember, for ax squared plus bx plus c, the x-coordinate of the vertex is negative b over 2a. Yep, that's an Algebra 2 thing that you should still remember. What's the b term in 2 minus x squared? 0, because there's no linear term to it. So that's how I know the vertex is at 0. But what's the problem with that? The vertex isn't in the domain. So I'm just going to do like 1, 1.5, and 2. So 2 minus 1 squared is 1. 2 minus 1 squared is negative 0.25. I think 1.5 squared is 2.25. And then 2 minus 2 squared is negative 2. And then the last piece is also linear. So I should have written that. So I just need 2 points there. One of them should be the endpoint for my domain, and then another one is whatever. So now I'm going to go ahead and graph this bad mama jamma. Okay. All right. So we have 0, 0, 1, 1. Now, I should make a note here that when I draw the 1, I should draw it with a open circle there. Why am I doing an open circle there? Yeah, because it's a strict less than inequality. And then I have that 0.13. And then here I have 1, 1. And again, that should have an open circle, so it's just attaching to where I had before. And then I had like 1.5 and negative 0.25. And then 2 and negative 2. So it's like doing this. It's pretty ugly looking. Just kind of have it do that. And leave that other point off. Just put it in after I drew it.
Why is that one?
Because if I look at the end, 2 has a greater than or equal to. So that's why the 2 got the 0.2, negative 2.
The one before.
Because that is also inside the domain,
Oh.
right? It's between 1 and 2. And then the last piece, again, I know that's going to need an open circle. So I have 2, negative 1. And then I have 3, 0. So it kind of looks like this. That okay there, Anise? Yeah. Okay. So again, the piecewise, you're just graphing one piece at a time. Is basically all it boils down to. Amanda?
How did you get 0?
So for this is going to be coming from here. How did I get 0? I guess that should have been negative 2, right? Thanks, Amanda. Still didn't match the other one, which was the point of it. Yeah, Mr. Coolidge forgot to square it, I think. Oopsie daisy. Paul?
Number 23, 2.6. I was kind of having like calculations.
That's not uncommon. 2.6, and you said which number?
Number 23.
23. Okay. So this one, I don't need to copy and paste. I can just write this down because it's just a whatever. So we have the limit as x approaches infinity of square root 9x to the 6th minus x over cube root x plus 1. Okay, so if I try to do a direct substitution and get like infinity over infinity, right? That's indeterminate, so I know I can't proceed that way. So what I'm going to do is I'm going to try to get all of the, if I look at just the numerator, and I think about the numerator as a whole fraction, I'm going to try to multiply the top and bottom of the big fraction so that the stuff in the numerator has only x's in their denominators. So I'm going to multiply the top and bottom by 1 over x cubed. Now, I can't multiply the top by 1 over x cubed because I can't multiply the x cubed into the radical. I need to have a radical around that. So 1 over x the sixth with a square root around it is the same thing as 1 over x cubed. So I'm just going to write it that way. Now when I multiply this through, I end up with 9 minus 1 over x to the fifth on top, and 1 plus 1 over x cubed on the bottom. So far, so good. Since both of these two functions are continuous over their domains, I can just apply the limit piecewise. So the limit of 9 is just going to be, the limit as x approaches infinity of 9 is 9. Okay. The limit as x approaches infinity of 1 over x to the fifth is 0. The limit of x approaches infinity of 1 is, and the limit as x approaches infinity of 1 over x cubed is, so this simplifies down to just 3. Cool with that, Paul?
Yeah, I just didn't know. Like, I know I was supposed to do something like that with like the y over x. I didn't know that. Yeah, I couldn't find it.
Yeah, no problem. Luke.
So that when you took it like this one, like you said, like, how can you do that? What law are you using?
So I'm using several, actually. I'm using, let me go back and look so I
Are
can.
you using the limit laws to do that?
Mm-hmm.
Okay.
Yeah, I'm using like theorem 8 from 124 to push the limit inside the square root.
Okay.
And then I'm using, these are way back in like 2.4 or 2.3 even. Yeah. And then I'm using the limit laws on page 99 to do the rest of it. But as long as you have like continuity, you can just kind of push that limit all over the place and just do what you need to. Anybody else? All right, dudes, let's finish up 2.8 then today. So where we had left off was we had extended this idea of calculating a limit specifically at one point, like we did up here in Blake's example, and have extended this to, what if I want to calculate the derivative of the entire function, so I get a derivative function back instead of just like a number or a value for the derivative. And what I want to do now is talk about the notation for a derivative. So to this point, when we've written a derivative, we've just written it as like the derivative of f of x, we've just written it as f prime of x, right? We could also write it as y prime. That's okay. Another very common notation is to write the derivative of y as dy dx. The d is short for like differential, which is kind of like borrowing from like delta y over delta x, the change in y over the change, oops, put those in the wrong spot. Change in y over change in x, like you did for slope. Except these aren't deltas because they're not change, they're instantaneous change, so they're like a differential. You could write like df dx, right? If you're talking about the derivative of f with respect to x, you could do d dx of some function f of x. People use the big D of like an f of x, or if you want to be specific about which variable you're differentiating over, you could put a little subscript there to imply the derivative with respect to x of f of x. And you're like, why does it matter what why would I differentiate over anything other than x? You'll see in the next chapter when we talk about implicit differentiation and start having an equation with like lots of x's and y's rattling around in it, and how that kind of changes the ball game. Tegan?
This doesn't really matter. Like, why are there so many?
So what you have to realize is when this calculus is kind of being formalized, it was like in the 1700s, and all different parts of the world were doing this independent of one another. So like if you wanted to know what was going on in Germany, not only did you have to get a paper from Germany to wherever you were at, you had to be able to read German also. And so like you have all these little pockets that use different notations to describe the same stuff. And they've just kind of like historically those areas have held on to that, and they've kind of creeped their way into, like standard notations. This is my best explanation for you. And in some instances, like the notation is like really convenient for what they might have been working on. And it's like when you see somebody else is doing something, it's like, oh, that beats the heck out of the notation I was using. Let me use that when I do this kind of a problem. But this notation is really tedious when I do this kind of a problem. So I'm going to go back and use the notation I had developed myself for that kind of, like it just kind of, you have a lot of that going on where we're just trying to be efficient. So like we have all these different ways to say the same thing. So I'm just going to pick the one that's convenient for the instance that we're working with. And I'll start mixing in some of these as we go so that it becomes a little less foreign if you see something weird, that we just get used to seeing some of these things. Those first three are probably the three most common ways of writing a derivative, though, at least at this level. All right. So a definition now. So we say that a function f is differentiable at a point A if the derivative at A exists and we say a function f is differentiable on the open interval from A to B if f of x is differentiable at every number in that interval. Yeah.
What do you mean by differential?
So that's just the first definition.
Yeah.
So that if I do that the derivative exists. So let's go back and look at an example. We did this, I think, last time. Let me pull this real quick because it is a really convenient example here for us. There it is. Let me pull this one. Okay. I'll put like a recall here. So if I look at my function, the domain for this function is the closed interval from 0 to positive infinity, right? If I go back and I look at the derivative now, the domain for this derivative is on the open interval from 0 to infinity, right? Because no longer can we have 0 because the x is in the denominator. Is okay with that? So what we see is that f prime of 0 does not exist, right? This implies that f is not differentiable at x equals 0. That's all we're saying. When we talk about being differentiable, it means that I can find the derivative at that point. Or if we're talking about differentiable on an interval, then it means I can find the derivative at all the points on that interval. Does that feel good? So the natural question here is, Mr. Kulik, we just looked at an example, and we saw that there's, like places where the derivative didn't exist, that were in the domain of f, but aren't in the domain of f inverse, or of f prime, right? So when might I expect that to happen? Okay. So there's really three situations that we need to worry about. The first instance is when we have a discontinuity. That's what's happening in our square root function there. If you remember, our square root function looks like this. So if we look at that leftmost point, the function is not continuous at that point. That's why the derivative is failing to exist, because there is no left-hand continuity there. It has right continuity, but doesn't have overall continuity. But there's lots of different types of discontinuities, right? So you could have, like a jump discontinuity. Derivative would fail to exist there. Or you could have like, a vertical asymptote situation. Derivative would fail to exist there. Although that's less of a concern, because why? The vertical asymptote's not in the domain of f anyways. I wouldn't expect it to be in the domain of f inverse if it wasn't in the domain of f, but worth stating. Everybody's okay with that? And those are the three, and then you have the removable, right? If you have like this, now, is the limit going to fail to, or does the derivative fail to exist there? What if we put it like that? You know, what if it's now it's defined for all values of x, right? Our function is that going to be a problem?
It's still discontinuous.
No, but there's the point that the
But that value for x is in the domain.
so it should be differential.
Right? So if I look here, what's the slope as we're approaching that point where the removal discontinuity is? It's the same as that slope would be, right? Derivative should exist there. So just because you have a discontinuity doesn't guarantee you that the derivative is going to fail. Okay?
You can't find the derivative. So you can find the derivative on the interval of that line. Find it at that specific point. How does that translate to a tangent line? How to jump discontinuity?
Because you're looking at the limit of the slope as you approach that point.
Right. If you but if you found the differential, the derivative of the function at the point or the when the discontinuity happens, what would the tangent line look like?
You wouldn't draw a tangent line through that point because there is no point there to draw the tangent line through. Right?
Yeah.
But there's still a slope associated with that missing point. Anyways, yeah. And then what else could happen? You could have a vertical tangent. So imagine you have some function f of x that kind of does this. If we pick a point, say there, and you try to draw its tangent line, it's vertical, right? What's the slope of a vertical line? Undefined. So that's a place where the derivative would fail because the slope doesn't exist there, right? It has no slope, the slope is undefined. And then the third one is if you have a corner. So our canonical example for that is the absolute value of x. And the place where the derivative fails to exist is here at 0. Because if I look at the slope of my tangent line here and the slope of my tangent line there, they're going to be different, right? As you're coming into 0. So from the left, it's approaching -1, and from the right, it's approaching +1. And then your limit fails to exist there, and since the limit can't exist there, then the derivative can't. So to just spell that out a little bit, let's look at this. So the limit as h approaches 0 of the absolute value of x and then let's look at the left, or this will be the right-hand limit. That's the case where x is positive. So using that, I can drop the absolute values everywhere. Which just gives me the limit as h approaches 0 of h over h, which is 1. Everybody's okay with that? Okay, so it's the limit of h approaches 0 of 1, which is 1. Okay with the extra step now? Okay. Yeah, it would be 0 over 0, but you have to you can simplify it down, right? That's why the 0 over 0 is indeterminate, because you can't, make up any slope you want for it, really. but that's not what we want to do. And then if we look at the left-hand limit, that's the case where x is negative. If I do the same thing, what do I get here? If I do the absolute value of x when x is negative, do that. Oops. What'd I forget? My limit. Do you guys know why I'm putting the negative sign there? Did you guys get that? Well, kind of. But if you think about, if you go back and think about the definition for an absolute value function, it's the piecewise, where if x is greater than or equal to 0, then it's just x. And if x is less than 0, then we make it negative x, right? So like the absolute value of negative 2 would be like negative of negative 2 or 2, right? If we negate everything that was negative, you get the positive. If you don't negate anything that's positive, you get the positive. That's how the absolute value is working. So that's where the negative signs are coming in. Is that okay? Anyways, if I do that, the same, almost the same thing happens, except what do you notice about my h here? It's negative, yeah. And because the limits don't exist, so this, so therefore, the limit here does not exist. So anytime you see a corner in the graph where you see that like, hey, the slope here is, you know, this value and the slope there is that value, everything's okay. Keep in mind that something like this is fine, right? Because it's not a sharp corner. If you draw the tangent here, both from the right and from the left, the slopes are going to 0, right? Because we're getting less and less steep as we move along, right? Less steep, less steep, less steep, less steep, less steep, less steep. What you have to worry about is like stuff like this, where it's you're getting a vertical tangent out of it, or stuff like that, where they're just not, the corner's too sharp. Is that okay, guys? All right. Next up, important theorem.
So because it's from the right, like, positive 1 and then 1 is negative 1. That's why it's
Yes, because the limits, the left-hand limit and the right-hand limit do not agree. Okay. So, if f is differentiable at a, then f is continuous at a. Okay, differentiability implies continuity. You have to have it. Everybody's okay with that? Okay. Is the converse true? If f is continuous at A, then f is differentiable at A. What do you guys think? This is false. What's your counterexample?
That last, the removable discontinuity? Sorry, John.
Well, I would, well, no, because those aren't continuous.
Oh,
Absolute value function, right? This is continuous at x equals 0, but not differentiable at x equals 0.
so going back to the first theorem, then how does like this jump discontinuity fit into that? Because that jump discontinuity is not continuous, but it is differential, isn't it? It's not jump discontinuity.
The jump discontinuity, no.
No.
The removable is the one that we were talking about, and I may not.
Oh yeah, you're right. I just got the name mixed up.
Yeah, let me think on that for just one more second. What if we talk about the contrapositive? Remember what the contrapositive means from geometry?
I want to make sure you know.
It's you both negate and you flip. So the inverse is the negation of the statement. The converse is the flip of the if-then. The contrapositive is both. So we'd say if f is not continuous at A, then f is not differentiable at A. And that one is true. This is true. Most definitions should be written so that them as well, the statement as well as its contrapositive should be true. I know the removal discontinuity thing. I think I was flat out wrong when we were talking about that earlier.
So that
I do not believe it's differentiable at the removal discontinuity.
Oh,
Yeah,
so,
my apologies there.
like this guy right here cannot differentiate.
Yes.
Okay.
Yeah, I think I got a little bit too. I thought too hard about it.
You've done too much math today.
Yeah,
If-
that's
Ooh, I have a question. So if the dot right there didn't exist, if it were not like removable, if it were just like a this does
Oh,
not
jump.
exist,
still shouldn't be differentiable.
still should okay.
Well, because it's not even in the domain of the function then.
Oh yeah.
Right.
Yeah.
So that was why I convinced myself that it was going to be differentiable there, is because the domain
Exists.
still was all real numbers. There was just that jump in there, and the slope should have matched up on the left and the right, but okay. Where is this kind of thing going to come in really handy for us? It's going to be using like more important theorems down the road, because differentiability is a shortcut to continuity, which we need to do like the intermediate value theorem or the squeeze theorem or things like that, right? So if you have differentiability, you automatically get continuity, and you can just apply those other theorems that you might need. Okay, so that little theorem there is not used a ton by itself, other than to like unlock other theorems. John?
But to prove something is like, so if the unit proof is continuous, by proving it's differential.
Likely what would happen is it'd be like, for a differential function f of x, show that blah 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 blah, and instead of like giving you continuity right away, you'd have to like recognize that differentiability does give you continuity, and then you could roll into like the intermediate value theorem.
Derivative of the function.
if you didn't have differentiability, you'd have to find the derivative and show that it existed over the interval in question. And then if you did that, then you'd have continuity as well. And that's typically going to be easier than continuity over an interval, because eventually it's going to become really easy to do the derivative and show that it exists over its domain, because you know how to do domains. And eventually we're going to be able to do derivatives really fast. And then it's, like, okay, here's a new function. What's its domain? Yep. Okay, so it's continuous over that interval. So. Okay. We have one more idea to talk about here. This would be about higher order derivatives. Whoa.
Sorry, guys.
That's
Drop
okay.
the ball.
So note when we have a function, we take the derivative, we get back a new function, right? That new function we call the derivative. If we take that derivative and we do the derivative of that, the resulting function we call the second derivative. Yeah.
Is the derivative always like 1 degree lower than the original?
Depends on the type of function it is.
Like in a quadratic.
So if it's like a quadratic, yeah. Yeah. So we can use all the same notations. We're just going to update and use 2 primes or use a squared or something. Okay. So let's say...
Why would you do that?
We'll talk in just a second about a situation where taking the repeated derivative tells you a lot of information about the actual real world situation.
Okay.
Yeah, that's a good question. And
Sorry, not.
No, it's a perfectly valid question to ask. I'm just going to ask you to table it because we're going to get there in just 10 minutes or something. I'll give you a real world example of which taking repeated derivatives actually gives you useful information that you'd actually want to talk about.
Okay.
All right. So if here's my function f of x, here's my derivative. If I want the second derivative, I'm just going to do the limit. And instead of using f, I'm just going to use f prime. So just apply my derivative formula. Actually, I'm just gonna foil this and do the substitution, everything all at the same time. Is everybody okay with that? And just less writing for everybody involved, right? And I'm going to distribute the negative as well. I'm just not going to show it. I'm just going to say it aloud that I'm doing that. And just write the simplified step here. Is everybody okay? So I plugged the x plus h into f inverse, foiled and distributed, and then distributed the negative sign across. I keep saying f inverse. I meant f prime. Plus h. Yeah. In the trig and pre-calc, we're talking about inverses right now, which has f to the negative 1 and it's f prime, and I just keep seeing the prime and reading inverse. You solve for x and then swap the x and y's. Yeah. It's easy, but no shame in forgetting. All right, let's combine some like terms. So all goes away. Notice that everything has a factor of h in it. That's everything left has a factor of h in it. So I can reduce those. When I do the direct substitution, I end up with 6x plus 3 times 0, or just 6x. So there's my f double prime, or the second derivative. If we did it again, what would we call that? The third derivative. And you know what the notation there is? Yeah. Well, there's no reason to get like, let's not get, you know, like crazy about this. You know, let's not invent a new notation every time we do something, right? So let's take the same function f, and we'll have our second derivative from before. What if we want to find the third derivative now? We just apply our definition of the derivative, but we use the second derivative. Yeah. And again, I'm going to plug everything in and do the simplifying kind of in one step here. Is everybody okay with that? Oh, rats. Fiddlesticks is a great one, yes. Okay, so if I combine like terms, the plus 6x and minus 6x cancel, and then I can reduce, because everything has a greatest common factor of h. So the limit as h approaches 0 of 6 is just 6. So I have then my third derivative is 6. If I want to do this again, what do you think I would call this? I think there's a u in fourth, right? This fourth, anyways. There is a fourth without a u, though, right? Like, henceforth. Like we're in old-timey land. So the notation here, what do you think the notation looks like? We just put a 4 up there.
Too many lines.
Yeah, it just gets too confusing.
Depending on how you write your fours, you're still making 4 lines.
Fair enough. But if you're doing like the 99th derivative, that notation becomes a lot more helpful, right?
That's kind of cool.
Yeah. So what is the fourth derivative going to be from our example?
Third.
If f of x was that same f of x, and or the third derivative was 6, you should be able to do this just in your head. Who's got it? Think about the graph. It's going to be 0. What's the graph of y equals 6 look like? Horizontal line. What's the slope at every point along that horizontal line? 0. What are all the derivatives after the fourth derivative going to be in this case? For this specific example, right? You could take the 10,000th derivative. It's going to be 0. Blake.
So, like, what is this? Like, so, this equation where we have x cubed minus x.
Mm-hmm.
So that looks like something on a graph. But what exactly, like what are we finding? Like, what information is like the 6, like the third derivative x is equal to 6? What does that actually convey?
Okay. So suppose that. Great. So suppose.
Is it the derivative? Oh, it's the derivative of the derivative line, isn't it?
So suppose that we have a physics situation, and that we have some function y equals s of t That's our position function. Okay?
Oh, I remember.
Yeah.
So, when we did the third derivative, you plugged in 6x to the x.
I didn't do that. I plugged x plus h into
Yeah.
here.
Oh, thank you. Look at that. Okay.
Because I was using the second derivative. Oops, that should be the second derivative there. That's probably what you're complaining about. Yeah, that was a typo on my part. Of course. Okay, back to Blake's question. We have some position function. We take the derivative of it. What is the rate of change of a position called? Velocity. Okay. And let's say we take the derivative of that velocity function. What's the rate of change of velocity?
Acceleration.
Okay, good. And if we want to take the derivative of that, what's the rate of change of acceleration called?
Sure.
It is. What'd you call me?
We learned it in physics.
We did that.
We literally learned that yesterday.
Yeah, we learned this yesterday.
So it's like how sharp the acceleration is. You can think about it like, you know, if you get like whipped around or whatever, I think is where the
So it's like acceleration.
not that I know that they have a name for.
Acceleration.
I mean, this is like
Dang.
applicable.
This is absolutely applicable to your physics class.
Why are we not being taught this in my physics?
Because it's algebra-based physics.
Yes.
It's the fact that
What if I did calculus? What would you say?
she'd kick you out.
Here,
Go on.
Luke, what we'll do is when we get a little bit further on and we learn the derivative rules, I'll show you the way that like all you need is one equation. We can derive all the other stupid equations that you need in physics from one.
So I can just get a 5 on the physics test.
I don't know about that, but it certainly seems doable to me. At least the motion side of it. I don't know what else you do in there.
We're just on velocity, acceleration right now.
Yeah.
That's it.
So the motion stuff matches really well.
It's like how fast
You
you
go. Okay. And then you get jerked.
Yeah.
It's your acceleration over time. It's just kind of weird to think.
And then there's like snap
Acceleration.
crack.
I really
Okay. So, Blake, here's a situation where like the second derivative, third derivative, etc., actually contain real information about like a real world phenomena. As we get further into chapter 3, we'll also talk about what the second derivative can just tell us about the graph of a function. Because there are things the second derivative can tell us about the graph of a function. Namely, what it's going to end up telling us is concavity. Whether it's bending like this way or that way. The second derivative can give us that information. So we'll be able to sketch pictures of our function from just what we know about the first and second derivatives.
So like these derivatives, like so obviously this last example, it ended with the fourth derivative being equal to 0.
Uh-huh.
But like so for more complex functions like that, like you can take more and more derivatives.
There are functions where you can take an infinite number of derivatives and the derivative is never 0.
Okay.
I can think about one function in particular off the top of my head that we all know that you could do that to.
Sure.
So think about a function that the pattern of change is always different.
Something with pi in it. Oh, exponential. Okay.
So
So that's like that's
so remember what E was?
not rational. Oh, that's true. It's not a rational
That's what E is.
number.
So what that means is like the rate of change at every step is e to the x.
Oh.
So each derivative of e to the x is just e to the x again,
Oh, okay.
which is like
Yeah.
which is like you can just keep doing that as long as you want. You're not getting anything different. This was just an aside, is all we're talking about right now. This was Blake asking questions that we're getting like 3 chapters ahead. But that's okay. I don't mind to do it. Yes, sir. Fall
Go to
first.
the bathroom right now.
Yeah.
I think.
No, well, I'm just done.
Whoa. Speedy lesson, guys.
Well, we didn't have that much left to do, and you guys are always a little bit quicker than 6th hour because my biggest homework question askers are in that section, and they're also my dress rehearsal for you guys. So like I'm doing kind of the exact same thing, so I just find like a little bit better way of saying it, and so it just goes a little bit faster for you guys. It's definitely because you guys are all much smarter.
Yeah, we're smart.
Yes, that's definitely what it is.
I don't like algebra.
I keep saying physics.
I'm messing with calculus, but it's all algebra, but I really am not messing with the algebra physics that I'm doing right now. It's just like, for some reason, I can't fit the numbers in the proper equations, and like, I understand the concept extremely well, but when I take the numbers and to apply them, I get something like slightly close, but never the same, and it's very important. It's like, it's not right, but- Yeah, no,